Welcome to Supply Chain Design course, week 9. This week, the topic is production and material requirement planning. Before discussing further about the two kinds of planning, we will read the introduction of chapter 12 of our textbook, as well as a case study of integrated operations and supply chain planning. Learning objectives for this chapter are explained in the first story of this chapter. A new operational planner, his name is Suresh Chandra, has just received the demand forecast data for the next year. His responsibility is to integrate aggregate planning, master production scheduling, and material requirements planning within the operational planning. The previous operations planning manager applied the following concept. First, sales and production plans were set up very early, typically in September of the previous year, and then agreements with customers and suppliers were signed. The problem with this system was that production and material procurement were not flexible enough to react to demand fluctuations. In addition, since the structure of the products was set up far in advance, the possibility of product individualization according to customer orders was missing. Suresh is supported by a trainee, Yana, to redesign the operational planning system. Yana and Suresh understood that matching demand and supply should take place as near as possible to the date when a customer order or demand is known. Yana made a suggestion. We could make production planning on a weekly basis each Friday for the following week when customer orders and demands are known. Suresh saw that the two problems here. First, it would be difficult to plan material requirements since many purchased items had quite a long lead time. Second, frequent production setups were expensive and not always possible for technological reasons. Yana, who understands how to make operational planning in different planning horizon or rolling planning concept, proposed to analyze which data should be set up for a long period of time, so-called design variables, and which data could be adjusted during the planning process, so-called control variables. This idea was really good. Suresh and Yana invited marketing, sales, manufacturing, and procurement managers to a meeting and jointly analyze the as-is planning process. They found out that rough demand data and production quantities for each month should really be known in advance. It was necessary to plan capacities and personnel, to make basic agreement with customers and suppliers, but at the same time, such data were not required in detail for each product. It would be enough to aggregate products into some product families according to marketing and sales interests. For manufacturing, it was important to know detailed data on production quantities at least 3 to 5 days before the beginning of the next month. This would be the basis for calculating master production schedules among all the production factories in the supply chain, which were interconnected and in the technological process. For procurement, such a timeline would also be okay for calculating material requirements and replenishing items from suppliers, taking into account lead times. Then, daily production plans could be set up. Suresh asked if it could be demonstrated that it would be possible to update production plans twice a month on the basis of new demand information. Yana also noticed that exact material specifications were not available for all products. This could create difficulties in procurement planning and result in missing items in productions. and very expensive breaks in manufacturing. Indeed, its product was composed of 2,000 parts on average. Even if one part was missing, delivery delay would occur. Suresh asked to rectify this problem and enter all the bill of materials into ERP system. In this chapter, we will learn basic methods of operational planning which will help Yana and Suresh to increase profit and to reduce cost. The operational planning and supply chain planning department is composed of the department manager, planning manager, dispatch manager, and supply chain analysis manager. The planning process starts with demand forecasting. On one hand, statistical methods such as time series analysis are applied. On the other hand, experts estimate numerous external factors at markets and suppliers. Demand forecast quality is crucial for planning quality, since small errors in demand forecast can lead to huge deviations in the planning and execution. A midterm forecast is available for 18 months, making it possible to start operational planning along the supply chain. Operations planning is based on the rolling planning procedure. Before planning production and material requirements, capacity, budget, and further constraints should be taken into account. After planning the master production scheduling or MPS, at execution phase, products are delivered to customer by transportation routings. Since demand forecast, production and supply chain plans are updated frequently. Rolling planning procedure is implemented. The rolling planning concept is based on the creation of a detailed MPS on a daily basis for 30 to 45 days for the whole supply chains. This MPS is updated every 15 days to take into account the dynamics of real execution. In this slide, we read a case study of the Sibur Group to know how to implement planning process. Sibur Group is a gas processing and petrochemicals company that owns and operates Russia's largest gas processing business in terms of associated petroleum gas or APG processing volumes. Sibur's business model is focused on integrated operations and the supply chain. The group has two operating segments, feedstock or energy and petrochemicals. The group's feedstock and energy segment comprises the gathering and processing of APG or associated petroleum gas, transportation, fractionation, and other processing of NGL, and marketing and sales of energy products such as natural gas, liquefied petroleum gas or LPG, naphtha, raw NGL, methyl tertiary butyl ether, and other fuels and fuels additives. The sales planning of the firm includes both the Russian and international market, and uses some of them as feedstock for its petrochemicals segment, which processes them into more than 2,000 different petrochemicals, including basic polymers, synthetic rubbers, plastics, and products of organic synthesis, as well as intermediates and other chemicals. The group operates 27 production sites, has over 1,500 big customers operating in the energy, automotive, construction, fast-moving consumer goods or FMCG, chemical and other industries in approximately 60 countries, and employs over 30,000 personnel. Linear programming can be used to find optimal mix within the product family. Basic quantitative method for SNOP is linear programming that allows allocate resources to demand in optimal way subject to capacity constraints. Finally, master production schedule specifies what is to be made and when in accordance with the aggregate production plan. The current slide contains planning decisions that can be divided into three: strategic, tactical, and operative planning. Strategic decisions are taken for a long period of time, typically for many years. Strategic decisions include strategic supply networks and capacity planning. Tactical decisions use information from strategic decisions and determining planning policies for some months. Tactical decisions need to balance sales and aggregate planning and quantity and cost planning. For sales and aggregate planning, the tactical planning includes sales and aggregate planning, which forecast the demand based on sales planning to produce aggregate production planning. A sales plan is a strategy that sets out sales target and tactics for a company business and identifies the steps a company will take to meet its targets. For quantity and cost planning, tactical planning includes production and distribution planning, inventory management, and procurement. Therefore, tactical planning matches supply and demand. Quantity and cost planning have shorter planning horizon by considering that a company can revise the plan earlier after reviewing actual realization of sales and aggregate planning. Operative decisions are taken in a weekly or daily manner for executing processes. Such a decomposition is needed since some data should be set up for a long period of time, so-called design variables, and which data could be adjusted during the planning process, so-called control variables. Some examples of different decisions at tactical and operative levels are presented in the figure in our slide. In front of us is a figure of manufacturing resource planning 2. From a management point of view, the tools are being used for planning the activities of all functions of a manufacturing company. In the planning process, MRP2 means the translation of business plans and demand forecast, including customer orders, into production plans and purchasing plans using planned orders in a real-time multi-level scheduling environment. MRP2 is a hierarchical planning approach. This means that decisions from the upper level are used as input data for the lower levels, as opposed to simultaneous planning, which is more complex. Based on requirements and constraints from finance, marketing, and manufacturing on one side and demand forecast along with capacity decisions on the other side, aggregate planning is achieved. Results of aggregate planning are further used for master production scheduling or MPS, which is the base for material requirements planning or MRP, lot sizing, procurement, order quantity calculation, and finally for short-term scheduling and routing. At each stage, balancing is mandatory to check that the results of the upper level may be implemented at the next level. In addition, the demand side at an upper level is balanced by a lower level to provide necessary resource supply to meet the demand side. Otherwise, incorrect calculations will be made throughout the planning levels. This could result in a situation where short-term daily schedules would have nothing in common with real demand. The wrong material could be purchased, and therefore we consider some important elements of the MRP2 concept. In order to achieve optimum aggregate planning to meet demand, the following information are required over the planning period. We need to identify production rate, the number of workforce required per unit of product, depending on the type of aggregate planning, whether we are allowed to employ workers over their normal work hour or not, what machine capacity utilization we need to use. If overtime were not allowed, should we subcontract unmet demand? Also depend on a company policy. Should we satisfy customer at 100% service level by meeting demand at any level of resource utilization, for instance workers, machines, and etc. Or we allow backlog by satisfying that unmet demand over the future periods. Finally, should we forbid from having stock out or allow it by taking backlog as a consequence? In the previous slide, we consider options for both demand and supply side, include production rate, workforce, inventory, overtime, outsourcing at supply side, and advertising, demand postponement, the customer service level, and product diversification at demand side. There are two strategies of sales and operational planning that we can use to make those tactical level decisions. Chase and level strategy. For chase strategy, a company uses capacity as the lever. The company has to meet the demand at any cost by matching output rates to demand forecasts for each period. Therefore, workforce level and production rate are vary to chase the demand. The second, that is a level strategy, a company uses inventory as the lever. The company benefits from having stable machine capacity and workforce level. However, the output rate is constant, and thus there is a chance of having stock out and postponing the demand at future periods. A way of solving the limitation, inventory is used as a buffer. Since the machine capacity and workforce level are stable, the benefit is the company can produce outputs at better quality and productivity. In SNOP, or Sales and Operational Planning, overall production quantities and capacity have been defined. In order to produce optimum production planning, a company has to decide on the optimum product mix within these aggregate volumes. The objective is to maximize the profit with regards to capacity limitation and known demand information. As a decision tool, a company can use linear programming or LP to support the production planning. A linear programming comprises an objective function to maximize the profit at optimum product mix within aggregate volumes. With regard to supply limitation to meet demand, a set of constraints allocate resources feasibly without violating capacity limit. Both objective function and constraints are expressed as linear functions. In linear programming model, There are two types of inputs: given parameters and decision variables. As a parameters in SNOP or sales and operation planning are products that we can produce, profits of each product, maximum demand of a particular product, maximum production capacity at a particular workstation, and capacity units or resource demand to produce one unit of a particular product. As an index variables, I stand for running index that identify products in SNOP. The objective is to find optimum resource allocations, for instance here machines and workers, to maximize the profit with regard to a set of production capacity constraints where the resource utilization for the entire n number of products cannot exceed the available capacity C total. The second constraint states that production of a particular product I cannot exceed its demand, but should not lower than zero, as stated in the third constraint. Let's see the following example. The table shows that machine 1 needs 45 times unit to produce both A and B by considering that A needs 0.3 time units and B needs 0.6 time units. Machine number 2 needs 25 times unit to produce both A and B by considering that A needs 0.5 time units and B needs 0.1 times unit. By multiplying constraint 1 and 2 by 5 and by minus 3, we get new equation that the multiplication between produced B and 2.75 cannot exceed 150. Solving the problem, then we have B is equal to 55.6, and therefore we get A equal to 38.8. Okay, now we have a second example in our slide. The demand in January for plastic windows of the type A and B is forecasted at 100 and 150 units respectively. The available capacity is 1000 time units. The price is $60 for windows of type A and $50 for windows of type B. For 1 unit of A and B, 5 and 4 capacity units are needed. For production A and B, components number 1 and 2 are required in proportion 40 by 60 and 70 by 30 respectively. These components are available in stock with 130 and 90 units respectively. The production of A and B implies material and manufacturing cost of $48 and $35 respectively for each unit. After reading this problem, we need to maximize our profit. A profit is defined as a net profit, that is, the benefit, the selling price, minus the total cost. In this case, we have the selling price per unit at 60 here for A and 50 for B, and therefore the net profit is for A equal to 60 minus 48 equal to 12. Is it correct? 12, yeah. The unit profit for A and B, it is equal to 50 minus here we have 35 and therefore we have equal to 15. Okay, now let's go to the next slide. Therefore, we have objective function 12xa plus 15xb to maximize the unit profit of A and B. The unit profit is 12 times the number of A produced plus 15 times the number of B produced. Alright? Now we have some constraints. For instance, here, production capacity constraint. Find here that for 1 unit of A and B, 5 and 4 capacity units are needed, and therefore for 1 unit of A and B, 5 and 4 capacity units are needed for A and B, and therefore A we need 5 and B we need 4, right? So 5xa plus 4xb less than 1000. Okay, and the next constraint is demand xa less than 100 and xb less than 150. We can see from here that the forecasted demand for A is at 100 and B at 150. Okay, and therefore A and B cannot be produced over than these numbers. And finally, we have non-negativity constraint that all production should be at least equal to 0. And we have also additional constraint for component. It coming from here that for production A and B, component 1 need proportion 40 by 60, and then we are here 40% and 60% for component number 1, and 70 and 30 here, 70 and 30, 74 from component 1 and 30 for component B, meaning that component 1 is produced should be produced from meaning that in order to produce product A needs 40% content coming from component number 1, 60% from component number 2. Also for B, in producing B, 70% comes from component 1 and 30% coming from component number 2. But the use of both components cannot exceed 130 and 90 respectively. Now we have to find the optimal product mix or component mix to produce optimally product A and B. First, we need to consider constraint number 1. Here, 5xe plus 4xb less than 1000. Let's suppose xa equal to 0. Then xb equal to 250. And then next xb equal to 0, then x equal to 200. And then we can plot 200 here, 200 here, and 250 here. And therefore we have here capacity constraint. Now we have the second constraint. xa less than 100, xb less than 150. Here, xa less than 100, right? xa less than 100, xa less than 100, xb less than 150. Okay? Okay. Now, a non-negativity constraint. Both should be higher or equal to 0. And therefore, only this region are feasible, but not here is no, here is no. Okay, and what else? Now we have component number one constraint. Okay, we do the same with SM2 production capacity here. If it is equal to 0, then XP should be equal to 130 divided by 0.7. Then we have this component number 1 constraint. Similarly also for component number 2 here. We plot all together this on a paper, and we have this region, we call it feasible region, because only in this region we can get feasible solution. And then we have also corner points. Here we have 1, 2, 3, 4 and 5 corner point. Corner point number 1, number 2, number 3, number 4 and number 5. So each coordinates here in each corner points here, we plug into our objective function, and which one give the highest value, that would be the optimal solution. And we found, for instance here, xp equal to 150, x equal to 0. So here we put 150 here, and here is 0, and then we have 150 times 2500. Here also 100 versus 0. Here maybe around 50 versus 100, 150. Here also maybe around 140 versus 80. Here 100 versus 100. I don't know. You can try to find and pick one give the highest profit. Okay, now let's go to the next example of applying linear programming to our capacity planning. First, it is given the profit of product P1 is 70,882 euro, and P2 is at 24 and 134 euro. Meaning that is the profit of 1 unit of P1 and 24,134 euro for 1 unit of P2. The lower and upper demand limits are 5, that is the lower, and 11 is the upper demand limit for P1. 8 is the lower demand limit for P2, and 17 is the upper demand limit for P2, respectively. The production coefficients are 7 for P1 and 11 for P2, meaning this is the cost coefficient for P1 and P2. The total machine capacity is 231 units. And then the task is that we have to formulate a linear programming model and solve graphically using ISO profit method and determine the optimal production mix. Okay, then let's go to the next slide. We know that the function is to maximize the profit, and therefore we have to multiply the unit profit with the amount of P1 produced and also the amount of P2 produced, and therefore we have the following: 17,982, this is the unit profit for X1, and 24,134, the unit profit for X2, and therefore we have here same X1 and X2. And the lower and upper bound 5 to 11 for X1, 5 to 11, so X1 cannot less than 5 or cannot higher than 11. Similarly for X2, cannot less than 8 but cannot higher than 17. And the capacity constraint saying that the maximum production capacity at 231 here, machine capacity 231, and for each unit of x1 need 7. It can be here can be the unit cost of production for x1 and unit cost of production for x2, right? And both x1 and x2 cannot less than 0, so the production capacity should be equal or more than 0. And therefore we do the same for as the previous example. We plot all equation here. For instance, here we have x1 should be higher than 5. Here x1 should be higher than 5. This is the line. And x1 should be less than 11, less than or equal to 11, less than or equal to 11. Okay, and the second product we have should be higher or equal to 8, should be higher or equal to 8 here, and should be lower or equal to 17. And then we have also here. Okay, and then what is left? The capacity constraint. Similarly, we put, for instance, here x1 equal to 0, for instance, and we have to calculate x2 equal to 231. Sorry, this is not really nice to write. Divided by 11, maybe around 11 point something. So it is 0.11 point something for x2. Let's see. For x2, yeah, 0, yeah, 21, yes, 21, and then 0 for x1. So it is the first point here, and then the next we have to reverse this equal to 0, and x1 equal to 231 divided by 7. I don't know how much. Yeah, around 33. So this is the second line, and then we connect these two lines all together by using these 2 points all together, and we can build a line here. All right. Okay. Now what the next step? The next step is that because all variables should be higher or equal to 0, and therefore the feasible solution should be within this region. It is not allowed, and here also not allowed. Alright, and what next? We need to calculate the objective function, and therefore the isoprofit line, meaning that we have to find which corner point, we call it these corner points, P1, P2, P3, P4, and P5 that give the highest profit. We can do it in two ways. First, we can find these values of these 5 points, and then we pick one, which one give the highest profit. Otherwise, we can compose this line equation, line equation, Okay, I just want to tell that this is a line equation. It's come from this equation. So if we take out x1 here, x2 equal to z minus 17 9 82 x1 divided by 24 1 3 4. Right? If we separate z and x1, we have a z divided by 24 134 minus 1 7 9 82 x1 divided by 2 4 1 3 4. Okay, yes, it is, and therefore we can put x1 x2 according to these 5 corner points and find z0, and the highest z0 will be chosen as the optimum profit, and we found from the example equal to 5 3 5 6 7 8. Okay, there is another way of doing of solving linear programming model, that is by using Excel solver. Let's take a look at this example. A company produces 3 products A, B, and C. The selling prices are $10, $20, and $30 respectively. Variable production costs are $3, $12, and $25 respectively. Demand for A is between 30 and 100 units. Demand for B is between 20 and 70 units. And demand for C is between 15 and 50 units. All the products need to be produced at 3 machines M1, M2, and M3 with total capacity for each machines are as follows: 300, 250, and 203 capacity unit. Production of the product A sees 2 capacity unit at M1, 1 capacity unit at 1, 2, so at M2, machine number 2, and 2 capacity unit at machine number 3. Production of product B sees 3 capacity units at M number 1 or machine number 1, 4 capacity units at machine number 2, and 2 capacity units at machine number 3. Finally, production of product C sees 4 capacity units at machine number 1, 5 capacity units at machine number 2, and 2 capacity units at machine number 3. Currently, the company produces 50 units of A, 25 units of B, and 12 units of C. The question is that, is the decision to produce 50 units of A the current decision, 25 units of B, and 12 units of C is optimal with regard to profit maximization? If yes, why? Otherwise, why not? So we have also need to find the optimal solution. Okay. Alright, now we start looking for the optimal solution of this current problem in our slide. Now we go to Microsoft Excel. In Microsoft Excel, there is a facility that can be used to find optimal solution by using linear programming. That is Excel solver. Using Excel solver, it is the most easy way to formulate linear programming model. Okay, let's start from the first sentence here. A company produces 3 products A and B and C. Let's say here A, B, C. Alright. Now we go again to our presentation. The selling prices are 10, 20, or 30. Selling prices 10, 20, and 30. Is it correct? 10, 20, 30. Okay. Now the variable cost 3, 12, and 25. 3, 12, and 25. Is it correct? 3, 20, and 25. Yes. Now we have demand for A in between 30 and 100. Right? Upper bound of demand, and here we have a lower bound of demand. 30 and 100 for A. The lower is 30 and 100 for the upper. And we have 20 and 70 for B. And for C is 15 and 50. 15, 50. Alright. The unit profit for each product as follows. This is net profit is selling price minus variable cost. We assume that there is no fixed cost in this problem. We do the same for B and C, right? D13 minus B13 and B14. Yeah, B13, B14. Alright? Yeah. Okay. C13 and okay, yeah. Okay, good. Now, what next? All the product need to be produced at 3 machines, M1, M2, and M3. Okay, let's go here. M1, M2, and M3, and we have here capacity. $300, $250, and $203. Should be here. 300, 250, and 203. 250, 203. Okay. For each product, for instance here, product A, this is 2 capacity units of at M1. So 2, 1, and 2 for M3. 2, 1, M2, 1, and 2. Should be M3. Alright, 2, 1, and 2. Yeah. 2, 1, and 2. Now B. 3, 4, and 2. Okay. So what about C? C says 4, 5, 2. 4, 5, and 2. Okay, now we go to profit function. Alright. Okay. 50. Yeah. Okay, the question is that whether the current decision is optimal or not. Alright. Okay, now we go first to define our profit function, that is equal to the net profit Okay, before formulating profit, we need to have that the first constraint number 2, constraint number 3. The first constraint state that the M1 produces maximum 300 units, right? So it is 2 times. Alright, before, yeah, we need to get also the decision variables here. That is how many A, B, and C should be produced. So in this is decision variables. And therefore, the profit should be equal to how many A produced times the net profit for A plus how many B produced times unit profit, net profit for B plus how many C produced time net profit for C. Alright? Okay, now we have completed our profit function um, development. And next we have to compose our constraint. The first constraint stated that M1 has capacity at 300 coming from 2. This is cost unit for A plus 3 cost unit times the unit, yeah, and C cost unit times the number of C produced. Alright, we do the same for here for constraint number 2 equal to 1 times A plus 4 times B plus 5 times C. Okay, now we go to the third constraint. Same we can calculate here. Times A plus times B plus times C. Alright? Okay, now let's go back to our problems here. That for each machine, so one for A, 2 capacity units at M1, 1 capacity unit at M2, and 2 capacity unit at M3. So for A, product A seizes 2 capacity unit at M1. Yeah, is it true? Yeah, it is 2 M1. Yeah, and for B, we have 3 capacity at M1. Also here 3 capacity at M1 exactly, right? And also here also 4 capacity at M1 for product C. Great. Now we can compose the optimization model by using solver, and we just press solver here. First we have to maximize profit, this profit, by changing the decision variables here. Okay, we have to delete one by one. It's come from the previous model. Okay, by changing A, B, and C to maximize P25, subject to, we have to add constraint that the A produced cannot higher than, because it is 101, the upper bound, then we have to put here 100. Should be less than or equal to 100. And then we have to add again, cancel, okay, we have to first add this A should be less than 100, less than or equal to 100, and then A again should be higher or equal to 30. We have to add again B should be less than or equal to 70, and again B should be higher or equal to 20. We have to add again C should be less than or equal to 50, and we have to add again C should be higher or equal to 15. Is that correct? Let's check. B32 should be less than or equal to B17, 130. Less than 7. Yeah, less than for B, less than C17, higher than C18. For product C should be less than D17, cell D17, or higher or equal to D18. Correct. Now we have to add additional constraints. For instance, here, the constraint here should be less than or equal to 300. Again, the second constraint should be less than or equal to 250, and the third constraint should be less than or equal to 203. Okay, what is missing? What equations miss in our formulation? That is non-negativity, meaning that we have to ensure that this should be higher or equal to 0. Okay? Yeah. We have to maximize P25, the profit, by changing these decision variables. Okay. Okay, now we have everything on our table, and let's start solving the problem. Okay? Here in our slide, we have a results for 3 decision variables. For A should be produced at 57, for B at 29.5, and C at 15. And then in addition to this result, actually we can also print the sensitivity analysis. And therefore we have another sheet as a report. Okay? Now let's check the answer from the previous decision. 50 unit of A, 25 unit of B, and 12 unit of C. Okay? Is it optimal? Okay, let's check. 25, 50, 25, and 12. 57, 29, 29.5, and 15. I don't think the previous decision is acceptable as a optimum solution, and therefore we have to propose the new solution here. Okay? Now let's check with the actual answer from our example. Is it the same or not? 57, 29.5, and 15. Yeah, I think that we have the same result with the values on our current slide. Okay, according to the suggested solution, optimal decision in regard to maximal profit to produce 57 unit of A, 29 unit of B, because it is integer, the product is discrete, not continuous. What is discrete? Discrete product. Discrete product meaning that the product cannot be make in fraction. For instance, like a table, we cannot buy half table. It should be 1, 2, or 3, right? But if the product is continuous, like oil or water, we can do it. In this setting, the capacity of M2 and M3 will be utilized to 100% according to the uh, solution obtained from our optimization. Here we have 57 should be produced. So C at 15, that is the lower bound, and 57 for A is still within the range. For B we have 29.5. Alright, so machine 3 should be utilized 100%. M2 would have utilization of 87.5. This decision would allow us to get a profit of $710 in setting the initial production 50 unit of A, 25 B, and 12 unit of C, and therefore the total profit is lower than the new optimization model, and therefore the profit increased by 16.4%. So 710, yeah, the previous one was 610, and therefore the increased profit is at 16.4%. Let's go for sensitivity analysis. So what is implied with this number? Here we have also sensitivity analysis, the same number here. Alright? The third column of the upper table shows the optimum production capacity for each product A, B, and C. So here. The first column, that is here, shows how much profit can change by decreasing or increasing production capacity for each product A, B, and C within allowable range. This is the allowable range. And the objective coefficient column shows the net profit per unit for each product A, B, and C here. Now we go to the lower table. The third column of the lower table shows the used capacity to produce products A, B, and C. So here, the used capacity. The shadow price column shows the possible profit decreases because of capacity of producing each product A, B, C increases by 1 unit. So it is a shadow price. So for instance, if the capacity of machine number 1 increased by 1 unit and the shadow price is 0, meaning that there is no additional decreasing in terms of profit. But different to machine number 2 and number 3, where the increase of 1 unit capacity for machine number 2 and 3 will decrease the profit by 0.33. Okay. After all, the 3 machines are still profitable at any capacity utilization within allowable increase or decrease range, as in column 6 and 7 here. So we can see from this the lower table that the capacity utilization for machine number 1 equal to 262.5 divided by 300, and that's about 87.5%. And similarly for 250 divided by 250, and therefore 100%. Also here 203 divided by 203, and we have also 100%, right? Okay. Now we go to the next slide. Okay, this is how to explain the table that I have explained just now. Now we go to capacity extension analysis. So here, the management of the company analyzed the sensitivity report results and observed that an increase in M3 capacity may potentially provide higher profit increase. So M3 capacity extension from 203 units to 250 units requires an investment of 100. So is it sensible to invest? Before proceeding for analyzing the model into solver, we have to keep in mind that if the profit is less than 100, meaning that it is not sensible. But if it's over than 100, then it is sensible. Okay? Now we need to solve LP model for new M3 capacity at 250 here. Before it was 203. It was 203. Now by changing to 250, we have different solution here. A should be plotted at 90, B at 20, and C at 15. Alright, before it was 57, 29.5, and 15. And the profit furthermore increased to 865, meaning that by adding more capacity to machine number 3, we have additional profit at 865 minus 710. It is equal to 155. Since 155 is higher than 100, then it is profitable. It is sensible to invest. Okay. Now the next problem saying that the sales manager can still observe that demand for product B and C is much higher as our production. The question is that what capacity do we need to cover maximum demand for all the products? So one possible option to answer this question is to solve the model against almost unlimited capacity, say 1000 units at each machine. And we can change here, it was 203, and then we can change to 1000. Here to 1000. To 1000, right? And let's see how many product A, B, and C can be produced. And therefore we have 100, 70, and 50. That is the maximum demand can be covered by increasing capacity to 100. However, the used capacity here, the used capacity is equal to 61% times 1000. So 610. 630 and 444, machine number 3. Yeah. Here it is the used capacity. And the utilization is 61%, 63%, and 44%. And the total profit is 15 and 10. Here we have also 15 and 10. If we look at limit report, how to get this? We can just go from solver and solve, and we can click limit and sensitivity all together. And then we have also here limit report. We have the same numbers here as compared to these numbers in our slide. In the columns target results, the limit report depicts the values of the objective function for lower and upper limit of the demand constraint. For example, It can be observed from figure 8, that is this table, that in the case of production quantity reduction for product A from 100 to 30 units, the total profit will reduce from 1510 to 1020. So by reducing from 100 to 30, we have also a reduction about our profit from 1510 to 1020. We can also observe that the lowest performance impact will have the reduction of product C production quantities. Here, only about one only about 100, yeah, 180 or 165 the reduction as compared to this one. This one around 400, sorry, around 490. But here is the lowest, and therefore C is the least sensitive product. All right. Okay, now we go to rolling planning. What is that? Planning at MPS level is typically done in a rolling or adaptive horizon. Rolling planning is continuous, event-driven, real-time replanning and control process. It uses not only simple open time slots, in contrast to incremental planning, but employs conflict-driven plan changes during the system execution. Rolling or adaptive planning is a method of planning in which a plan is modified periodically by a change in the system parameters or the characteristics of control influences on the basis of information feedback about the current system state, the past, and the updated forecast of the future. In adaptive planning, the precision of planning decision decreases while moving away from decision point. Now we can see here that, for instance, we have the dash line, that is the process execution trajectory as planned at the instant time t0, and this line, the thick lines, represents the real process execution. So in the current state, there's adaptation point. There is a change in the process to minimize the gap between the actual condition, actual process, real process execution here and here. We would like to minimize this gap, and therefore by the end of the current state, again these two lines coincide and make a new line that is coincide one of another, meaning that the process is again under control. All right. So now we go to rolling planning in the next page, saying that in adaptive planning, the precision of planning decision decreases while moving away from the decision point. So we can see here, for instance, at time t, that is time when the decision is taken, and by the passage of time from t to t plus 1, the gap between realization and the planet capacity or planet activities are wider, and therefore planning decisions become faster with increasing distance between the decision-making point. This may be interpreted as a sequence of inserted funnels. At certain intervals, the plans are updated. The fuzzy part of the plans becomes precise, and a new funnel for the further process course appears, meaning that if at this period we try to make adjustment to minimize the gaps between plan and realization, and therefore the gap can be minimized. By the passage of time from t equal to 1 to t equal to 2, again we can see there is a wider gaps as compared to the previous check period t equal to 1. So such an approach provides the required flexibility with regard to dynamics and uncertainty. Hence, adaptive planning implies problem resolution and redefinition through the learning process rather than problem solving. This allows us to interpret planning and scheduling not as discrete operations but as a continuous adaptive process. The adaptive planning procedure can be interconnected with the adaptive procedure. This allows reaction in the real-time mode to necessities for replanning due to disruption in supply chains. If there is not sufficiently full information about the system and operation dynamics, certain key operations and events must be determined, of which the uncertainty of states does not allow operations plans to be formed. As a result, a number of alternative operation dynamic scenarios can be elaborated. Further, with time, the uncertain at the time of planning operation states become certain and possess certain characteristics or parameters. Okay, we will continue our lecture for week number 9, but in session 2, and the topic is about materials requirement planning or MRP.